A generative adversarial network, GAN, represents a category of machine learning frameworks and stands out as a key approach to generative artificial intelligence. Conceived by Ian Goodfellow and colleagues back in June 2014, GANs operate on the basis of a zero-sum game involving two neural networks that vie against each other. The dynamics of this setup mean that what one network gains, the other loses. By leveraging a training set, the GAN method learns how to produce new data possessing the same statistical attributes as the initial set. For instance, if trained on images, GANs have the capacity to create fresh images that exhibit a level of authenticity discernible to human viewers, sporting numerous realistic features. Despite its original intent as a generative model for unsupervised learning, GANs have proven valuable for semi-supervised learning, fully supervised learning, and reinforcement learning as well. The fundamental principle of a GAN hinges on the concept of indirect training, facilitated through the discriminator, a separate neural network responsible for gauging the realism of the input, which also undergoes continual updates. Unlike being trained to reduce the distance to a specific image, the generator's objective is to deceive the discriminator. This unique approach allows the model to acquire knowledge in an unsupervised manner. GANs draw parallels to mimicry in evolutionary biology, embodying an evolutionary arms race between the two networks. The original generative adversarial network, GAN, defines a game where two players, the generator and discriminator, interact within a probability space. The generator aims to match its output distribution closely with a reference distribution to minimize the objective function, while the discriminator tries to distinguish between real and generated data samples to maximize the same objective. In this zero-sum game, the generator is tasked with creating synthetic candidates, which the discriminator evaluates to discern their authenticity. The generative network maps latent space to data distribution, while the discriminative network learns to identify real data from generated samples. The generator's goal is to deceive the discriminator by producing novel data samples that are indistinguishable from real data, thus increasing the discriminator's error rate. Training involves presenting the discriminator with real data samples until it reaches a satisfactory accuracy level, while the generator trains to generate better samples that fool the discriminator. Using separate backpropagation methods, the generator and discriminator networks improve iteratively. In image generation applications, the generator is typically a deconvolutional neural network, whereas the discriminator is a convolutional neural network. GANs differ from alternative generative models by being implicit and not explicitly modeling likelihood functions or latent variables corresponding to samples. They can generate complete samples in one pass through the network, unlike other models that require multiple passes. Additionally, GANs, being universal approximators, have no restrictions on the network function types used, making them asymptotically consistent in training processes. The mathematical theory behind the methods involves probability spaces with a sigma algebra in modern probability theory based on measure theory. For a more rigorous definition in the GAN game context, each probability space, denoted as triple omega b mu ref, defines a GAN game, where the generator's strategy set is P of omega b. This consists of all probability measures mu g on the measure space omega b. The discriminator's strategy set is defined as the set of Markov kernels MUD from omega b to p of open bracket 0, 1 close bracket, b of open bracket 0, 1 close bracket, where b of open bracket 0, 1 close bracket, is the Borel sigma algebra on the interval 0 to 1. In the generic version of the GAN game, the discriminator's strategy set encompasses all Markov kernels. Mu subscript capital D from omega to probability of 0, 1, while the generator's strategy set involves arbitrary probability distributions, mu subscript capital G on omega. However, the optimal discriminator strategy against any mu subscript capital G is deterministic, leading to restricting the discriminator's strategies to deterministic functions, capital D from omega to 0, 1. Typically, the discriminator function is a deep neural network, while the generator's strategy, theoretically any computable probability distribution, is commonly realized as a push forward. Mu subscript capital G equals mu subscript capital Z, composed with capital G inverse. In this setup, the generator's strategy is often denoted simply as capital G, with Z distributed according to mu subscript capital Z, implicit. The objective of the GAN game can be defined mathematically as capital L, open parenthesis, capital G, capital D, close parenthesis defined as expected value of x distributed according to mu subscript reference, open bracket natural log of capital D of x close bracket, plus expected value of z distributed according to mu subscript capital Z, open bracket natural log of open parenthesis 1 minus capital D of capital G of z, close parenthesis, close bracket. The GAN architecture features two main components. The first component involves optimization as a game where the objective function is minimize over capital G, maximize over capital D of capital L, open parenthesis capital G, capital D close parenthesis, a departure from the typical optimization of the form minimize over theta of capital L, open parenthesis theta, close parenthesis. The second component entails breaking down mu subscript capital G into mu subscript capital Z, composed with capital G inverse, serving as a reparametrization technique. This distinction is significant when contrasting GAN with prior generative model learning techniques, which struggled with complex probabilistic computations in maximum likelihood estimation and related approaches. The reparametrization concept was also explored by Kingma and Welling, as well as Resende and others, evolving into a general stochastic backpropagation method utilized in the variational autoencoder. In the context of move order and strategic equilibria within the GAN framework, it is conventionally assumed that the generator moves first, followed by the discriminator. This sequence frames the minimax game as minimize over mu subscript capital G, maximize over mu subscript capital D of capital L, open parenthesis a mu subscript capital G, mu subscript capital D, close parenthesis equals expected value of x distributed according to mu subscript reference, and we distributed according to mu subscript capital D of x, open bracket natural log of y close bracket, plus expected value of x distributed according to mu subscript capital G, and y distributed according to mu subscript capital D of x, open bracket natural log of open parenthesis 1 minus y close parenthesis close bracket. The equilibrium concepts vary based on the order of moves. Equilibria when the generator moves first and the discriminator moves second, when the discriminator moves first and the generator moves second, and the Nash equilibrium under simultaneous moves all exist and are equal in the original GAN game. However, for broader GAN games, these equilibria may not necessarily exist or align. When both the generator and discriminator in a GAN have access to their entire strategy sets, a distinct global equilibrium point is established. However, this equilibrium becomes uncertain when their strategy sets are limited. In practical scenarios, the generator can only utilize measures of the form mu subscript capital Z composed with capital G subscript theta inverse, with capital G subscript theta referring to a function computed by a neural network characterized by parameters theta, and mu subscript capital Z representing a readily sampled distribution like uniform or normal distribution. Likewise, the discriminator is restricted to functions of the form capital D subscript zeta, where capital D subscript zeta is computed by a neural network defined by parameters zeta. These limited strategy sets represent a minute fraction of the overall strategy space available to them. Even if an equilibrium exists in such conditions, discovering it involves exploring the vast high-dimensional realm of all potential neural network functions. The conventional approach of employing gradient descent to pinpoint the equilibrium frequently proves ineffective for GANs, often resulting in the game collapsing into various failure modes. To enhance convergent stability, some training tactics commence with simpler tasks, like generating low-resolution images or straightforward images of a single object against a uniform background, gradually escalating the complexity of the task throughout training. This methodology effectively implements a curriculum learning scheme to address convergence challenges. GANs often face mode collapse issues, where they struggle to capture the full diversity of the input data, resulting in missing information. This phenomenon, sometimes humorously referred to as the Helvetica scenario, is illustrated by the example of a GAN trained on the MNIST dataset, generating only digit 0 images, despite the dataset containing multiple digits. Mode collapse can occur when the generator progresses too quickly relative to the discriminator, leading to suboptimal outcomes. Specifically, if the discriminator remains constant, the ideal generator output would be limited to maximizing the discriminator's output on a given input. During GAN training with the MNIST dataset, if for a period the discriminator shows a slight preference for digit 0 over other digits, the generator may exploit this preference, ultimately getting trapped in a local minimum once the discriminator adapts. Some attribute this issue to a deficient discriminative network overlooking crucial patterns, while others blame the choice of objective function. Various solutions have been suggested to address mode collapse, but it remains an ongoing challenge, as even advanced models like BigAN 2019 have not completely overcome this issue. The authors of BigAN acknowledged the occurrence of mode collapse and suggested allowing it to happen in later training stages, relying on the model's overall training to produce satisfactory outcomes. To enhance GAN convergence stability, researchers introduced the 2-timescale update rule, TUR, adjusting the generator's learning rate to be slower than the discriminator's. This approach aims to prevent the generator from quickly steering the discriminator into unexplored areas without incorporating its accumulated knowledge. The proponents demonstrated that training a broad category of games, including the GAN framework under TTUR, leads to convergence towards a stationary local Nash equilibrium, assuming reasonable conditions. Additionally, they recommended leveraging atom stochastic optimization and evaluating GAN performance using the Frechet inception distance to mitigate mode collapse and assess model effectiveness. When the discriminator learns at a significantly faster pace than the generator, it may reach a point where it can almost perfectly distinguish between the generated distribution mu subscript capital G subscript theta and the real data distribution mu subscript reference. Consequently, the generator, denoted as capital G subscript theta, could encounter challenges as it faces consistently high losses regardless of the adjustments made to its parameters theta. This situation leads to the gradient with respect to theta of capital L, open parenthesis capital G subscript theta, capital D subscript zeta close parenthesis approaching 0, causing the generator to struggle to make progress, a scenario known as the vanishing gradient problem. Essentially, the discriminator's proficiency becomes a hindrance, leaving the generator unable to make meaningful advancements due to the limited impact of small parameter changes in gradient descent. One prominent approach used to tackle this issue is the Wasserstein-GAN methodology. The evaluation of generative adversarial networks, GANs, commonly revolves around metrics such as the inception score, IS, and the Frechet inception distance, IGFED. The IS assesses the diversity of the generator's outputs based on classifications by an image classifier, typically inception V3. Conversely, the FID quantifies the similarity between the generated samples and a reference dataset using a trained image feature extractor, like inception V3 without its final layer. Numerous research papers introducing novel GAN architectures for image synthesis often highlight their performance improvements over existing models in terms of FID or IS benchmarks. Another evaluation criterion gaining traction is the Learned Perceptual Image Patch Similarity, or LPIPS metric. This method involves the utilization of a learned image feature extractor, F subscript theta from image to real numbers, superscript N, which is fine-tuned through supervised learning using a set of triplet samples. Open parenthesis, x prime, perceptual difference of x and x prime close parenthesis. Here, x represents an original image, x prime depicts a perturbed version of it, and perceptual difference of x and x prime quantifies their dissimilarity based on human perceptual judgments. The fine-tuned model aims to approximate the norm of f subscript theta of x minus f subscript theta of x prime as approximately equal to perceptual difference of x and x prime. Subsequently, this refined model helps establish the LPIPS measure as LPIPS of x and x prime defined as the norm of f subscript theta of x minus f subscript theta of x prime. Various other assessment methodologies are discussed in the literature for comprehensive evaluation of GAN performance. Conditional generative adversarial networks, or conditional GANs, differ from standard GANs by incorporating additional information to generate samples under specific conditions. This means that a conditional GAN can produce outputs tailored to certain inputs, such as creating a cat face based on a dog image. In a GAN framework, the generator creates a probability distribution mu subscript capital G on a given space omega. However, in a conditional GAN, the generator generates distinct probability distributions mu subscript capital G, open parenthesis C, close parenthesis on omega for each class label C provided. For instance, in the realm of image generation like ImageNet, the generator should be capable of producing a cat image when given the class label cat. The concept of conditional GANs was introduced by the authors in their original paper, highlighting that by supplying labels to both the generator and discriminator, a GAN can seamlessly transition into a conditional GAN setup. The objective function for conditional GANs involves the probability distributions over classes, real images, and generated images. Notably, in 2017, a conditional GAN successfully learned to craft images across 1,000 classes from ImageNet. Various alternative architectures have been explored within the GAN framework, showcasing the adaptability of this model. Examples include the Deep Convolutional GAN, DGAN, which relies solely on convolution-deconvolution layers, the Self-Attention GAN, SAGAN, incorporating self-attention modules, the Variational Autoencoder GAN, VAGAN, utilizing a variational autoencoder, the Transformer GAN, TransGAN, deploying a transformer architecture, and the FlowGAN, employing flow-based generative models for efficient likelihood function computation. These diverse architectures emphasize the flexibility and potential of GANs in image generation tasks. Additionally, GANs have been experimented with alternative objectives by modifying the loss functions for the generator and discriminator. Variants include original GAN with non-saturating loss and original GAN with a maximum likelihood approach. Hinge loss GAN is another variant, and least squares GAN introduce different loss functions to enhance training stability and convergence speed. Each variant offers unique advantages and considerations to further optimize the performance of GAN models in diverse applications. The Wasserstein GAN introduces modifications to the traditional GAN framework by restricting the discriminator to measurable functions with bounded Lipschitz norm. The objective function for this network involves calculating the difference between the discriminator's predictions on generated and real data samples. This alteration aims to combat mode collapse issues commonly encountered in GAN training. Notably, the creators of Wasserstein GAN reported no instances of mode collapse during their experiments. Another approach, the adversarial autoencoder, AAE, combines elements of autoencoders and GANs by training a discriminator to distinguish latent vectors from a specified distribution like the normal distribution. In contrast, InfoGAN enhances conditional GANs by introducing a mechanism that allows latent vectors to be split into noise and label components. This technique encourages the generator to maximize the mutual information between the label and the generated output. To tackle the intractability of this information measure, InfoGAN employs variational mutual information maximization, indirectly optimizing a lower bound of the mutual information. The objective in an InfoGAN setup involves a game with 3 players divided into 2 teams, the generator and Q versus the discriminator. The overall goal is to minimize a specific objective function defined by the components of the InfoGAN game. The standard generative adversarial network, or GAN, uses a generator function denoted as G that maps from a latent space omega sub z to the image space omega sub x. This mapping process can be described as decoding, where each latent vector z belonging to omega sub z serves as a code for an image x in omega sub x, and the generator's role is to decode this information. Expanding upon this idea, the concept of training a network to perform encoding was developed, resulting in the formulation of an autoencoder that utilizes an encoder-generator pair. This concept was further developed in the bidirectional generative adversarial network, known as BGAN architecture, where the game is defined within 2 probability spaces, omega sub x with measure mu sub x and omega sub z with measure mu sub z. In this framework, there are 3 players organized into 2 teams, the generator and encoder on one team and the discriminator on the other. The generator and encoder aim to minimize the established objective, whereas the discriminator seeks to maximize it. The objective function incorporates the logarithm of probabilities related to the strategies of the players and the distributions across the 2 spaces. The CycleGAN architecture offers a unique approach aimed at translating content between 2 different domains, for instance, transforming images of horses into zebras or converting night cityscapes into their daytime counterparts. This method involves 2 probability spaces, omega sub x with measure mu sub x and omega sub y, with measure mu sub y, each representing one of the domains needing bidirectional translation. The components in play include two generators, G sub x, which maps the space omega sub x to omega sub y, and G sub y, which maps omega sub y to omega sub x. Additionally, there are two discriminators, D sub x designed to map omega sub x to a range between 0 and 1, and D sub y designed to map omega sub y to the same range. The BigAN is a self-attention generative adversarial network developed with a massive scale, featuring up to 80 million parameters, to generate high-resolution images from the ImageNet dataset, achieving dimensions of up to 512 by 512 pixels. It utilizes a variety of engineering techniques to facilitate effective convergence throughout the training process. In cases where the available training data is limited, traditional methods often fail to accurately capture the reference distribution, denoted as mu subref. To address this challenge, data augmentation becomes essential for improving training on smaller datasets. By implementing semantic-preserving transformations T, which map omega to omega via data augmentation, the original GAN framework undergoes a modification. This adjustment results in a revised GAN framework that accounts for a new distribution NMEREF E, produced by applying Tx to X, with X sampled from EMREF and T from M-trans. The application of data augmentation to both real and generated images is essential for training effectiveness. The utilization of invertible data augmentation is emphasized in the StyleGAN2 ADA paper for optimal results. For instance, in the context of generating ImageNet images, employing invertible data augmentation ensures the generator maintains image orientation fidelity while training. The concept of invertibility in data augmentation is underscored by its ability to uphold the original distribution and optimal strategy for the generator, crucial for achieving desired results in GAN training scenarios. The Markov kernel, represented as K subtrans within the framework of data augmentation for arrow images, can be depicted as a stochastic matrix. Notably, this matrix is invertible if the probability P is not equal to 1/4. In a continuous context employing the Gaussian kernel on images within a 256 by 256 pixel space, the transformation K subtrans involves convolving with the density function of a specific Gaussian distribution. This convolution remains reversible because convolving with a Gaussian acts similarly to convolving with a heat kernel. By adjusting the time variable suitably, it is possible to recover the original distribution. Additionally, techniques like SynGAN explore the boundaries of data augmentation by training a GAN using only a single image and utilizing a multi-scale approach to perform augmentation. On the other hand, the StyleGAN series, including the progressive GAN model, evolves GAN training gradually from small to large scales in a pyramidal manner, with generators and discriminators progressively added at each stage to generate images of increasing resolution. To ensure smooth transitions between stages, a blending technique is employed, exemplified by smoothly integrating new layers into the GAN game as it progresses in scale. StyleGAN 1 is characterized by a progressive growth mechanism reminiscent of progressive GAN, blending neural style transfer concepts. With the foundation of a 4x4x512 array, each image in the generation process undergoes styling through a series of style blocks. These blocks employ a style latent vector through an affine transform, akin to Gramian matrices in neural style transfer. Following this, noise is introduced and standardization occurs. During training, typically one style latent vector is used for each image, occasionally employing two for mixing regularization to enhance each style block's independence in stylization. After training, multiple latent vectors can be input into style blocks, with the lower layers dictating large-scale styles and the higher layers fine detail styles. Additionally, merging styles from two images is achievable by projecting each image into the style latent space and feeding them into the appropriate style blocks, creating a composite image blending large-scale and fine detail styles. StyleGAN 2 builds upon the foundation of StyleGAN 1, enhancing it by utilizing the style latent vector to modify the weights of convolution layers, effectively addressing the blob issue. Further advancements were made with StyleGAN 2 ADA, incorporating invertible data augmentation and dynamically adjusting the augmentation level based on an overfitting heuristic to adaptively improve performance. StyleGAN 3 refines the technology further by resolving the texture sticking challenge observed in generated videos. By leveraging insights from the Nyquist-Shannon sampling theorem, this version introduces stringent low-pass filters between generator layers to ensure faithful processing of pixel signals in line with continuous representation, while also enhancing rotational and translational invariance using additional signal filters. As a result, StyleGAN 3 effectively eliminates the texture sticking dilemma and produces images with seamless rotation and translation capabilities.